Alright, welcome back to Meteorology 101. This video, I am going to cover the Skew-T chart. This is just an overview. We're not going to get into major plotting, decoding, analysis. That's for a later video. Got a lot more to go through before we hit that point. But I have been talking about Skew-T charts and mentioned that quite a bit. So I figured I'd put something together that would just explain the chart, what it is, what it looks like, and what all the lines mean. So this video may be a little short, may go longer. We may jump into some chart analysis again and continue the video there. Let's see where we end up and how long this one takes. So the Skew-T, with the overview, we got parameters found on the Skew-T can be useful for forecasting clouds. You can forecast cloud levels based on what type of lift you have, at what point, what height condensation will occur. Precipitation, the types of precipitation, specifically based on freezing level, warm layers, cold layers, how thick they are, and determining your precipitation types: rain, snow, freezing rain, sleet. You can actually determine all that from this chart. Atmospheric stability, you can look at your lapse rates. If you have inversions present, or the temperature decreases with height in general, if that decreases with height past the standard level, the standard rate, then your lapse rates are a lot steeper. Then you can determine stability. Plus, you have many algorithms on this chart that plots we can do. That we can look at the LI, the SSI. There's a lot of stability indexes that we can look at to determine stability atmosphere. Moisture content, we can look at the mixing ratio lines, and plus we can look at the temperatures and dew points once they're plotted, and we can see how close these temperature and dew point are to each other to find out areas in the atmosphere in the vertical that are saturated or close to being saturated. Turbulence, we can look at our wind scale and that wind staff. We can look at our wind plots and we can see how far winds are veering or backing with degrees, and how the wind speeds are changing with height, and then what speed velocity change we have within a certain amount of feet from each other to determine light, moderate, severe turbulence. Icing, based on the freezing level, we can determine where the icing is, and with the stability indexes, we can determine if there's going to be severe weather. All right, start with the isobars, the horizontal brown lines. These are lines of equal pressure. They're represented horizontal solid brown lines, and they're spaced every 10 millibars. Pressure levels are labeled every 50 millibars at both ends and the center of each line, so you can pretty much look all along that line and see what millibar level you're at. So when you get the data comes in encoded, but it'll tell you if you're the mandatory levels of where those, what the radio sound sent back for the pressure at those mandatory levels. So the mandatory levels must be plotted. You have a lot more on the decoded or the encoded Skew-T data that will be between the mandatory levels, but those mandatory levels, the radio sound knows is a must. That data must be sent. So you can look anywhere on across that line and see where your millibar lines are, so you know what level you're plotting at. So you're plotting temperatures, dew points, and winds at that point. So the labels are in brackets at each end of the appropriate isobars. The ICAO, that's your standards for aviation weather. For that station, it's the weather station standards, and the heights are printed under the corresponding isobar to the left side of the chart, and feet in meters. So these are standard heights. We're looking, like I said, we're looking at the mandatory levels, what we call them, is basically your surface, which that's just a surface observation. You get your winds, temperatures, dew points off of that. Then 1,000 millibars, 850, 700, 500, 300, 200, and typically 100. So, like I said, you have a lot more plus between those standard levels, and then you'll come up with a whole plotted chart. Once we get to the end of this thing, I got some pictures of plotted charts. I don't have one big complete one, but like I said, this is just an overview. Like the isotherms, the lines of equal temperature, and they're represented by a straight, solid brown line sloping from the lower left to the upper right of the chart. And the lines are printed in 1 degree intervals and labeled every 5 degrees. And there's a Fahrenheit scale printed along the bottom for quick conversions. I don't have this thing shrunk down to see that Fahrenheit scale. All you can really see is the numbers on the lines that are going from the bottom left to the upper right, and then you start at your 0, and then you can count over every degree. They're labeled, and they're labeled every 5 degrees, but they're in 1 degree intervals. So if you, on the Skew-T chart, it is the temperatures aren't rounded. They're basically, when you're plotting these, if you have 10.1 degrees Celsius, you're going to go 10.1 degrees Celsius on the plot. The dry adiabats, the lines of constant potential temperature. Dry adiabats are slightly curved, solid brown lines sloping from the lower right to the upper left of the chart, and they represent the rate of change in the temperature of the parcel of dry air, unsaturated, rising, or sinking. They are printed at 2 degree intervals, and they're labeled at 10 degrees along the 1030 millibar isobar. So the dry adiabats are how an air parcel rises. It's an unsaturated air parcel rising or sinking on a standard atmosphere. So it's unsaturated. That's why it is a dry adiabat. So that is, you just have to remember the dry adiabats are unsaturated. And then we go to the moist adiabats. This is saturation adiabats. Represented the rate of change of the temperature of the parcel of a standard air rising or sinking. So this is basically, if you had standard atmosphere, 1013.2 millibars is standard atmosphere, and you rose those air parcels from that standard atmosphere up the saturation adiabats, and then you can see what levels that they would become saturated at. So everything on this chart is based on standard atmosphere. A solid green line sloping up from the lower right to the upper left of the chart, and near 200 millibars they parallel the dry adiabats. So they pretty much run right with the dry adiabats once you get in those way into those upper levels. About 200 millibars. I mean, you're talking about 38,000 feet, or a little bit higher than that. So really, you're not going to get many clouds, much saturation up there anyway. So that's why they pretty much parallel with the dry adiabats at that point. They're printed in 2 Celsius degree intervals, and are labeled 2 Celsius degrees of 530 and 200 millibars. All right, saturation mixing ratio, those are the dashed lines. Now this represents the ratio of grams of water vapor per kilogram of dry air. Basically, the parts of the water vapor per 1,000 parts of dry air. So on a standard atmosphere, remember everything on this chart is standard, and they're one of the best measured actual moisture present in the atmosphere. So they're slightly curved. It's a little hard to tell, but they are curved. Dashed green lines sloping from the lower left to the upper right, with numerical values printed at 970 millibars. So this line is important for the mixing ratio. You can do a lot of calculations with this, where your dew point temperature, if you follow the saturation mixing ratio up, crossing the temperature line, or you get your temperature line crossing the mixing ratio, then you can do a lot of calculations on this thing. We'll get into a little bit of that, not a whole lot on this video. All right, the wind staff. This one is, you can see the one on the left is plotted, the one on the right is blank. So for each level that you plot a wind direction and speed. And then you can look at this, just looking at this chart going from the surface up, you can see that the winds are veering and increasing in speed with height until you get way up into the upper levels, and then they just go light and bearable at that point. Way in the upper levels, but the you can see that these winds are veering and increasing with speed as you go up. No significant changes here to determine any significant turbulence or anything, just looking at that chart. Okay, so the standard atmosphere, the lapse rate shown as the heavy brown line in the center of the chart, starting at 1013 millibars. That's your standard atmosphere at 15 degrees Celsius. You use to compare the actual temperature conditions to standard atmosphere. So when you look at the Skew-T, when you plotted Skew-T, and you can see your temperatures and dew points and your lapse rates, and that this is the standard pressure decreasing with height. So you can, this lapse rate, it's a standard lapse rate. Anything steeper than that can indicate an unstable environment, and then you can use those calculations for severe weather also. But this is your standard atmosphere. The higher you go up, the less density, so the less pressure. So you have a decrease in pressure with height. Okay, the condensation levels. Now these are a little bit of calculations you can do on this chart from your dew points, temperatures and dew point lines, and then using the lines on the Skew-T. So your lifting condensation level is the height at which an air particle becomes saturated if lifted dry adiabatically. But it has to be forced with something. Frontal lift or graphic lift. Something has to cause that lift. It can't just be from convection or surface heating. The CCL, the next one, is the convective condensation level. That is strictly the heated from below, surface heating, and then bringing that air particle up, and at what point saturation occurs, and the cloud bases of cumuliform clouds. And that, if you watched any of my other videos, we did talk about cumuliform types of clouds. The cumuliform is an unstable cloud because it's caused by the heating of the surface. So as the heat goes up, the heat's kind of mixing around, and it is an unstable environment. Convective temperature is the temperature of the surface must reach for convection to begin. And then the mixing condensation level is the lowest level in a layer, mixed by turbulence. So it has to have mixing. Something's got to mix the atmosphere, and which saturation occurs after complete mixing of the layer. And it's used for forecasting cloud bases in areas with strong mechanical mixing. So areas that you have turbulence, then you can use this calculation to determine what your cloud height is going to be based on that mixing. That's going to change some of the other factors. So just by having that turbulent mixing. Okay, so here's a little bit of a chart. This is kind of generically done just to show you how to get some of these readings. And if you follow the dew point up the mixing saturation mixing ratio line, then where you intersect with the temperature line is your CCL. That is your convective condensation layer. So if you have daytime heating, you have nothing else playing a part in pushing that air particle up, just strictly heating on the surface. The sun is out, it's a sunny day, you get the heating rises, and that dew point, the mixing from the heating is, this is the layer that the base of the clouds are going to be just from the convective condensation level. So if you look down at the bottom of that, you have an LCL. Now where your temperature dew point follow the mixing ratio line up, and then you take your surface temperature, you follow the dry 80 back up, and where those two intersect is your LCO. So if you was expecting frontal passage, or you have orographic lift, you live near the mountains, then when an air partial is forced up by an outside force, then that is your lifting convection level. All right, the T sub C that on the right hand bottom corner, that is the convective temperature. So if you go from the LCO, follow it dry adiabatically down to the surface temperature, then that is the temperature, that convection, that the surface would have to reach for convection to occur. So they start right at the 1,000 on this chart. That bottom dot for your temperature could be lower than that. That would bring your convective temperature even higher. So if you notice, you have 30, 32, 33 degrees Celsius. That's pretty hot. So about 91 degrees. So that would be, definitely, if you're in the 90s, you can have a convective activity just on surface heating. So. And then I think that's pretty much all we have on this chart. Let's go to inversions. So layer in the atmosphere where the temperature is either isothermal, which there's no change in temperature, or increases in height. So your lapse rate, you basically have a negative lapse rate. So if you look at this chart, get my mouse over here, that is your inversion. You have a increase in temperature with height. If you actually go to the Skew-T, go back to the Skew-T, our temperature lines are the brown lines from the lower left to the upper right. So plotting that line, the temperature line, as it pushes up toward the right, you're increasing with temperature. You're increasing temperature with height. So then that creates your inversion. Now, you'll typically have fog associated with those inversions. This one's a little high. This is just a generic example of an inversion. So there's no change in height, temperature with height. Which actually, this is kind of deceiving, because if you look at the Skew-T chart, this is just a generic chart. This isn't representing the Skew-T chart. That's why that line is straight up. But if you're actually on a Skew-T chart, then your temperature, the base of that inversion is here. Then the temperature lines actually go at an angle. So your upper temperature would have to be here for to be no change in temperature with height. If you're going straight up, there's actually, on a Skew-T chart, that's actually a decrease in temperature with height. So don't let this confuse you. Radiation inversion and surface-based inversion formed by rapid cooling of the air in contact with the surface of the Earth. So what you see here typically is like it clears out at night. Overnight, you have radiational cooling, the surface of the Earth cools the air above it and brings that down to the dew point. Brings that temperature, the surface temperature, down to the dew point, then condensation occurs at that point. And then you end up with a surface inversion where it's cool on the surface, right there at the surface, but your upper air temperatures haven't changed, so they're still warm from the day before. So you have that increase in temperature as you go up into the atmosphere. So then that creates a cap, holds all that moisture to the surface, and any light winds, just 3 knots or so, just enough to give it a little bit of mixing, then you can get that radiation fog to form. A substance inversion is mechanically produced inversion formed by adiabatic warming of the sinking air. So as air sinks, it compresses and warms, and then that temperature would be, so this right here would be, as this air sinks, compresses, warms, and then creates an inversion, and it caps the surface. so you can get that subsidence, that warming just from compression. So the dew point will rapidly decrease at the base of the inversion as it is sinking, as the sinking air warms and dries out. And significant in that it suppresses convective activity. So this caps everything down. It will suppress convective activity. Any inversion would, because it's a stable layer aloft and or even from the surface, but it's a stable layer and it will suppress convective activity. We talked about a couple videos ago was mentioned the loaded gun, and that was an inversion present, and then you have advection, pumping warm moist air underneath that inversion, horizontal advection, and then the temperature at the surface cooling, or the upper part of that inversion cooling, or the temperature at the surface increasing, breaks the inversion, and then the convective activity is no longer suppressed, and then that atmosphere can just explode into the upper levels and create a pretty much an air mass thunderstorm just right out of nowhere and all of a sudden. Frontal inversion, so transition zone between the cold air mass and the warm air mass above it. Used to calculate the frontal slope and intensity, and seen as a layer of weak warming and where the dew point increases through the inversion. So if you have a cold front coming through, the warm air riding up over the top of that cold front, and you launch a balloon through that, then you're cooling, getting colder with height, and then as soon as you hit that point of the top of that cold air mass, and then you would basically have no change in temperature with height. Actually, you would have an inversion, you have an increase in temperature with height, and then you would actually start cooling again in the upper levels. So that would create your inversion with a warm air mass over a cold air mass. This isn't a stable environment, so that's where the inversion basically is a stable environment where you're increasing temperature with height. We live in an unstable environment where temperature naturally decreases with height. So when you get an inversion, you have just a stable layer, and that's what caps all this stuff off. So it suppresses any convective activity. The winds will back with height through an inversion. So if we see it on that wind barb, that chart with the winds, I said they were veering. They were basically on a, when you plot the winds, those directions, if they're starting to turn clockwise, they're veering with height. If they turn counterclockwise, they are backing with height. And we'll back with height through the inversion if the cold front is depicted, and the winds will veer with height through an inversion if a warm front is depicted. So if you look at if you have frontal passage, warm frontal passage or cold frontal passage, then your winds will either veer or back with height. Alright, so that ends this video. I'm going to do a separate video on chart analysis, so let's go ahead and end this one. And like I said, later on we'll get into a little bit deeper into Skew-T analysis. Let me go all the way back to the top. So there's the best picture I have right now of a Skew-T. That's actual Skew-T I have. That there's your Fahrenheit temperature scale. So those are labeled in Fahrenheit. They're labeled in Celsius, so you can convert pretty easily right there. And then the horizontal lines are your standard atmosphere lines of equal pressure, and then this is a standard atmosphere that represents a standard atmosphere, and then you have your moist adiabatic lines, dry adiabatic lines, and then obviously all your temperature lines, and your temperature and dew points are plotted on the temperatures. So just an overview there. Like I said, this was just an overview on the Skew-T. Try to get you familiar with it, and later on we'll decode the data, and we'll actually plot one of these charts, and then learn a little bit deeper and try to do some analysis. So that'll be a much longer video. So alright, once again, thanks for watching, and give me a thumbs up if you like the video, share the video, help me out, and get your head in the clouds.